Hello everyone, I am Yunjia from University of Chicago. It's a great pleasure to be able to meet you all at Parity-Violating from Home conference, and I'm quite grateful to be given this opportunity to share with you an ongoing work I have with Liantao, Zhongzhi, and Yiming on parity-violating signals from cosmological collider. Our journey begins with the cosmic inflation, which is a rapid expansion of the universe during a very early stage of the universe. Since it happens at such an early stage, it's quite natural to expect that inflation happens at a relatively high energy scale. In fact, this energy scale, known as inflationary Hubble, according to our current experiment, can be as high as 10 to the 13 GeV, which is inaccessible to ground-based collider experiments. Therefore, the Cosmological Collider program is to try to use this rapid expansion to understand heavy particles that are not available in our usual collider experiments. Once these heavy particles are produced, they are likely to interact with the inflaton, which is the scalar that drives inflation. And it's the fluctuation of the inflaton field that becomes the seed of the large-scale structure that we see nowadays. As we gather more and more cosmological and astrophysical data on large-scale structures as well as cosmological backgrounds, cosmic microwave background, the hope is to use these data to constrain new physics that happens at very high energy scale. I believe for this audience, it's not quite necessary to convince you that parity violation in its own is interesting. Nonetheless, I would like to provide some motivation for why I want to combine parity violation with cosmological collider. There are studies showing that these parity violating signals tend to have relatively low background compared to their parity preserving counterpart. But to me, what's even more interesting is that I believe these models are well motivated theoretically. In particular, these models tend to have what I will call a chemical potential enhancement, which I will elaborate later. And that means not only you will get a lower background, you will now get a sharper signal just coming from considering these models over the usual cosmological collider models. I keep drawing this analogy between particle collider and cosmological collider. As it turns out, they are really similar, even in terms of the workflow. So what I'm showing you now is the workflow comparison between a cosmological collider study and a particle collider phenomenology study. So we all start with a Lagrangian, which encodes a reasonable model. And then we draw some diagrams, which we will call Schwinger-Keldysh diagram on the cosmological collider side, but they are just comparable to the Feynman diagram you draw. Now, to get observables, we usually compute something in momentum space. In our case, these are called spectrums, bispectrums, and trispectrums. The inflaton fluctuation that we compute in the end are in fact not quite what you get from these large-scale structure survey data or CMB data. Therefore, we have to convert them into these endpoint correlation functions of galaxy density fluctuation or other density fluctuation that we can easily probe in position space. So as you can see on the right-hand side, we have a well-established industry on how to get from model to the detector in the context of understanding particle physics. But I believe now it's the right time to think about what happens on the left. How do we improve the pipeline and even get a very nice workflow going from models for a cosmological collider all the way to what we can observe in large-scale structure data. In this project, what we considered is a spin-1 exchange model. It's basically an abelian Higgs model where my scalar has a large VEV, thus gives my z prime, which will be the exchange particle, a large mass. We'll also introduce this ZZ tilde type coupling, just because it can generally happen in these type of models well. And I'm going to couple these ZZ tilde coupling to a time-dependent background, which is constantly rolling. By that I mean theta dot d theta dt is a constant. If so, then we can transform into momentum space and solve the equation of motion. The first two terms gives us the familiar quadratic p squared minus m squared type term, whereas the last term is really the interesting term. The combination c naught times theta dot, which I will lump up and call that c, is the chemical potential. And then we get this epsilon ijk term, this Levi-Civita tensor, encodes the parity violation in our model. And then we have this derivative, which in momentum space is nothing but the z prime's momentum. This term not only gives us parity violation, but also give us this linear dependence on the z prime momentum, which modifies the dispersion relation of the usual quadratic dispersion relation. This is what we call the chemical potential. And in fact, if you solve the equation of motion, you find something quite interesting. You will find that the z prime will have different enhancement or suppression dependent on this chemical potential. In particular, the negatively polarized state of my z prime will now enjoy an exponential enhancement. And this compensates what usually is a Boltzmann-like type of suppression coming from massive particle exchange for cosmological collider studies. Therefore, these parity-violating spin-1 exchange really can potentially provide the leading discovery channel for that is already imprinted, perhaps in large-scale structure data. Now that we know how z prime is going to propagate in an inflationary background, we'll talk about how z prime can talk to the inflaton fluctuation. We're going to consider the following interaction, where we'll have two inflaton fluctuation talking to one z prime, and the propagator of z prime itself already encodes the parity violation term, this epsilon ijk term, and then these type of coupling will allow us to contract the epsilon ijk to external momenta of inflaton fluctuation. So in general, the trispectrum of the full spin-1 exchange model will look like some complicated function that depends on the external momenta k1, k2, k3, k4, as well as the propagator momentum ks. But then it will be multiplied to this particular tensor structure that is quite striking. And this comes from this contraction of epsilon ijk symbol, which encodes the parity violation. The end goal of this project will be go to the position space data. But the drawback of going directly to position space is, of course, that a lot of intuition we have in momentum space might be lost just because of the complicated Fourier transform that we will do. So what we did is that we pull out another toy model, a simpler model that perhaps is easy to compare with a full model. The toy model we're going to consider is just to replace a complicated prefactor, this factor, with a relatively simple factor. This is, in fact, just the equilateral shaped template, or you can think about it as a 4-point contact interaction. That is, if your inflaton has self-interaction through derivative-type coupling, that prefactor is precisely what you would expect. But equilateral shape templates themselves are not really parity violating. Therefore, we just multiply this parity violating term as a way of parametrizing these parity violation template-like contact interactions. Now, people might think that although this sounds challenging, maybe it's just a Fourier transform. How challenging is this Fourier transform? As it turns out, the real challenge comes from the fact that we are integrating over a large phase space. That is, we have to integrate over these 12-dimensional integral coming from the summing over external momenta of inflaton fluctuation. Just as an example, this integral, let's say that I discretize it on my computer using grids, and I take 10 grid per dimension. That means I need to sample over 10 to the 12 points. And that's a lot to be handled with at least our computational resources. This actually has been proposed that maybe we can consider some simpler model that contains a separable type trispectrum. By that, we mean that the trispectrum can be a product of functions. Each function, each factor, really depends on one external momentum. Then instead of integrating over 12-dimensional these complicated Fourier transforms, you're really integrating over 3-dimensional ones, and then you have 4 of them that you just multiply together. This is more tractable computationally. However, this is quite restrictive from a theoretical perspective. In general, a full model with a particle exchange cannot be factorized, at least for its trispectrum, into such a simple form. Nonetheless, with the Schwinger-Keldysh formalism, we actually identify a rather compromising position that allows you to do something that's kind of quasi-separable. The enlightenment really comes from the fact that when you draw a diagram, what you do is really that you have to do 2 more conformal time interval. These integrals come from that you have to integrate over these scale factor dependence in your interaction terms, or on the other hand, you can think about them as saying that during the expansion of the universe, heavy particles like this Z prime are created, and then propagate for a long time until around tau 1 that they decay into 2 inflatons. And what we observe in the end is not decay at a particular time, but decay at arbitrary time before the signal reach the surface tau equals 0, which is the boundary or today. Thus, we have to sum over all of these possibilities. Now, this integral is nice because these propagators for the inflaton field generally contains a rotating this phase factor that goes like e to the ik tau. What's usually handled in theoretical computation is that we weak rotate tau to it such that we get, instead of an oscillatory phase factor, we get an exponentially damped factor. That means we only have to sample over small tau so that we can capture the most important part of the correlation. This is kind of intuitively understandable because late time correlation perhaps will be more striking compared to if these interactions happen way too early. This is not the only advantage of using Schwinger-Keldysh diagram, because now with this diagram we can see that these propagators for these external legs, for these inflaton fluctuations, now really factorize, at least factorize, become separable for the external momenta. And they tend to be similar, if not identical, so we can recollect or reuse them during numerical computations. Now that we have these terms being separated, we just have to integrate over conformal time tau 1 and tau 2, which you know is really important only around late time. And this is basically how we set up the entire numerical computation. We first compute the momentum part more or less quasi-analytically until we have these conformal time integrals, and then we plug that back into our computer and allow computer to take care of the Fourier transform as well as transfer functions and map the trispectrum to the endpoint correlation function for a galaxy data survey. Now we're ready to show you the result. What I'm going to show you will be a position space data, and it will be presented in this endpoint isotropic function basis. You can think about this as basically a multipole expansion, and what I'm going to show you will be the multipole expansion's coefficient. These multipole will be labeled by discrete multipole index L1, L2, and L3, the lowest being L1, L2, L3 equals 1, 1, 1, and the highest will be L1, L2, L3 to all the way to 3 or 4. In fact, from the data side, there are already studies using these bases to to represent large-scale structure survey data such as BOSS data. And what we are trying to do is trying to push from a theoretical side to get all the way through these pipeline to get to see if we can compare the result with the data. What I'm going to show you next will be 3D plots. Each of this box is a particular combination of L1, L2, L3 multiple coefficients. All of these spheres, all of these dots will be placed at different positions corresponding to different R1, R2, and R3. The size of the sphere will tell you how strong the correlation is, and the color of the sphere will tell you whether the correlation is positive or negative. I'd like to also mention that when L1, L2, L3 is the lowest, then it roughly corresponds to the kind of position space counterpart to the momentum tensor structure we saw previously. Instead of having K1 cross K2 dot into Ks, we get R1 cross R2 dot R3. And here is our result. On the left, you see the full spin 1 data, and on the right, you see the toy or the equilateral contact term data. What's interesting for this plot is really that I would like to direct your attention to the upper left versus lower right for each of these models. You can see that for the full particle exchange model, you get correlations for the lowest angular beam, but even go to higher and higher angular beams, you still get some non-trivial correlations. It seems to populate all of them. Whereas on the right, for a template model, where you just get a contact term, it seems that the correlation is the strongest for the lowest angular beam, and then for higher order angular beams, they are not as pronounced as what you'd expect. So this point is quite interesting, because we believe this also kind of tells you that even if we fit our data with templates, that helps us to extrapolate how large the non-Gaussianity might be, or where to see if there are new physics there, it might actually not quite capture what the full physics, the exchange of some particle, might actually be encoded in terms of large-scale correlation functions. And at this point, I'd like to thank you for paying the attention, and I'm going to leave the summary slide here, and I'm looking forward to chat with you during asynchronous or synchronous discussions. Looking forward to meet you. Thank you.